Good day. I'm going to be talking about machine learning in plain English, and this is going to be the first part of a multi-part series. In this particular session on machine learning, I will be discussing just the plain intuition behind the different machine learning algorithms. It will not include any tiresome math or difficult or laborious programming in it. It'll just be the plain logic and intuition behind the different machine learning algorithms, the metrics, and how we go about it. So let's get started. How do we learn? How does a human being learn? How do we learn a new skill or a new something new? So for example, if you are trying to learn a musical instrument or if you're trying to learn swimming, what we tend to do is we tend to keep repeating a particular piece or a score from a music on your particular instrument. And as we repeat, we keep monitoring how we play, either by ourselves or we have someone listen to what we play, and we make small corrections to how we play. Similarly, when we are learning to swim, as we learn a particular stroke, we tend to observe ourselves and try to make minor adjustments in our technique so that we become better and better at that particular skill. Here is a formal definition of machine learning, which has been coined by Tom M. Mitchell. He says a computer program is set to learn from an experience E with respect to some class of task T and the performance measure P. If its performance at these tasks as measured by P improves with experience. So this is just a formal definition of what I had already mentioned with respect to learning a new instrument or learning to swim. We try to learn from experience. We try to measure how we perform in each of our attempts and try to improve on that. And as we improve our performance, we can say that we have learned that particular task. And this is exactly the definition that Tom M. Mitchell has given. So first, let us look at regression. Regression is one of the most common methods that is employed in machine learning, and we can create pretty sophisticated machine learning models with regression. There are different types of regression: linear regression, multivariate regression, polynomial regression, logistic regression, etc. for different tasks. What is regression? Simple linear regression is a method, a statistical method, that allows us to study the relationship between some specific target variable and a set of input variables. These input variables are either known as predictor, explanatory, or independent variables. They are also known as features. The other variable which we are trying to estimate, y, is regarded as the response outcome dependent or target variable. So we have a set of input variables which are the predictors, and we have an output variable. So we need to be able to estimate if there is some relationship between these input variables and the specified outcome or response variable. That is essentially what regression is all about. So let us take a simple example, a toy example, if you may. How does the salary of a person vary with age? Is there a relationship? Assuming that we are able to collect data of different people across a cross section of society, and we plot their age and their salary on the y-axis, would we be able to determine if there was a relationship between age and salary? So just assuming that we had this sort of plot where we had age on the x-axis, 25, 35, 45, 55 years old, and the salary in either rupees or dollars or whatever currency you may be interested in. And let us assume that we see a plot like this. Intuitively, a human brain can easily come up with a relationship, a curve which kind of passes through most of these points and says, and we can figure out intuitively. But can we actually make a machine be able to estimate this relationship between age and salary? What would we need to do for a machine or a program to be able to determine this relationship? So let us try to look at it a little bit more in detail. So this is the same data we have. What is essentially happening in the back of our mind, even though we can intuitively see a relationship between age and salary, the unconscious mind is trying to fit various possibilities to this data, right? So we are probably trying to see a fit like this. We can see it's a very poor fit. It does not pass through any of the points. Maybe something it passes through some of the points. Maybe we get better, and finally we come to a point, a line like this, a black line, which seems to represent this data set pretty well. Okay, and this is essentially what we're happening, even though we are able to instantaneously come to this conclusion when you see this data. But typically this is what is happening, and we would like our machine or any program to be able to come up with such a method. So what would we need to do? So this is linear regression. So basically linear regression is essentially we are trying to fit a straight line. Okay, it is not a curve, it's just a straight line that gives the best estimate of this ratio between this age and salary. So what exactly are we trying to do? And clearly we can see that if we take a second order polynomial, a quadratic function, it will probably do a much better fit of this particular set of points, and it'll probably be something like this. And we could go for higher polynomials. Typically the higher the degree of the equation you take to represent your independent variable and the dependent variable, the more closely it will follow this particular set of points. And you can go for a degree polynomial of degree 3 or degree 4 or degree 9, and we'll try to trace the points as closely as possible, right? But that is not what we want to do. We will come to what exactly machine learning is, and it is not exactly, we're not trying to fit the curve to all the points. There are two important measurements that we use in machine learning to determine how well we are able to fit the data. One is called the bias. When a machine learning model, when we say the machine learning model has a high bias, then that model does not take into account the variation in the data. It is kind of, like has a fixed kind of tendency towards the data. It does not look at the variation in the data, and it is fixed. So it's like a bias. You can look at it even in a very normal way. And variance is when the machine learning model takes into account all the variation in the data set and tries to follow the data set very closely. Okay, and it does not generalize well. So here we see this. I have the same age and salary data in these three graphs. Which do you think is the best fit? I mean, what would you choose as a machine learning model that does a good justice of the data? Clearly, if you look at this one on the left, it has a high bias. It tries to go in a straight line, doesn't follow the way the data kind of curves in any way, and we call this an underfit, or we can say it as a high bias. If you look at this particular graph on the right, it tends to follow the data a bit too close. This is when we use a high order polynomial, and this is called an overfit, and it has a high variance. Clearly this data curve which we use to estimate the data is a very good fit, and this is a good fit. It has a moderate bias and a variance, and clearly we can see that it generalizes very well on the data set. So what exactly are we doing when we say we are having a good fit? What is happening is, let us assume that this black line is the estimated line and these red points are your actual data points. A good fit is when if we drop the perpendicular lines from these actual data points to the estimated line, and we sum up these distances, uh, and we make sure that the total sum of the distances is the lowest, then we can say that it is a good fit. Clearly, if it follows very close to the point, then the perpendicular distance between that actual data point and the estimated line will be very small. And typically we don't use just the distance of the data point to this estimated line, rather we use the square of the distance, because if you just use the distance absolute value, if you just use the distance, then we would have distance which are on the positive side and some on the negative side, and they may add up and they may appear to be add up to 0, and it may look like it's a good fit, but actually we want the total sum of the squares of the distance to be the smallest possible value. And so hence this measure, where we take the square of the distance from the data point to the estimated line and average the square of this distance, is known as the mean square error. And if we are able to ensure that this mean square error is the lowest, then that would be a good fit. We can be confident that our estimated line is a good fit. Okay, so let us take another toy example. Assuming that this is our data set, and we draw different lines. So first we draw this blue line which actually passes through the data set, and we take the distance. It is actually on the blue line, so the mean square error is 0. Then we take this green line, then we take the square of the distances from this point to this thing. So it has some value which is for this slope 0.5, and then we take for the slope this orange line, that is where the slope is 0, because this is actually on the x-axis, and we take the mean square error. And finally we take this red line which has a slope of minus 0.5, and we measure the distance, mean square error distance from this actual data point to this estimated line. And if we plot the distance, this distance, mean square error, or is also known as the cost, with respect to the different slopes, we will find that we have a nice curve, a parabolic curve like this. And our job, as I said, a good fit is when we have the lowest mean square error between the estimated line and the data points. So how do we determine this lowest mean square error? If we have some knowledge of calculus, this is a fairly straightforward problem. We know that when you are trying to find the minimum of a function, if you take the derivative of the function and find the point where the derivative is 0, that is, it is actually parallel to the x-axis, that is the lowest point in your function. So that is exactly what is being done in machine learning. We don't really take the derivative, but we take an arbitrary point on this particular curve, which is this curve, as I said, is the plot of the mean squared error and the model parameter. That is, for different slopes we compute the mean square error. That is, for different slopes of these lines, green line, blue line, yellow line, red line, each has a different slope to the x-axis. We compute the mean square error, the square of the distance from the actual data point to this particular point, and we plot this curve. Now if we take an arbitrary point on this side here, this blue point here, this slope is actually positive, because you can see this slope is actually positive, is about 60 degrees or something. And to be able to go in the direction where the mean square error is 0, we would actually have to update our model parameter in the negative direction of this slope. So what happens is, if we are at this point, we will try to move in the opposite direction of this slope, whereas if you are on this right side of this on the left side of this curve, then the slope is negative, and we will try to move towards you will again update this parameter so that we move towards this where the slope is 0. So we take small steps along this curve after choosing an arbitrary point, so that we move towards progressively towards this point where we get a local minimum or where the slope is 0. At this point we will get the values of the model parameters which we should use for our estimated function. So gradient descent, and this approach is known as the gradient descent. It is a way to minimize the cost of the model parameters by updating the parameters in the opposite direction of the gradient. We move against gradient to find the local minimum. So here is a little bit typically so far we have taken a very simple example where we have taken age and salary, where we had just a single parameter versus a target variable. But in reality you could have 2, 3 or any number of input variables, features, predictors, etc. to some output response or target variable. Here we have two parameters to the model, and we again take here this j is called the cost function. Again we could also call it the mean square error, and we if we plot this mean square error or cost with respect to the model parameters, we'll actually get a complex surface like this. And as before, we will need to find the points on this surface where the cost, that is the cost or the mean square error, is the lowest. That is typically a point like this. And how do we do that? We do exactly the same way. We use gradient descent. We choose an arbitrary point on the surface. So let us say we choose a point somewhere here, and then we find the slope or the gradient at this point, and then we move against the gradient. If it is positive, we'll move in this direction. So we'll slowly start traversing this surface so that we start edging our way towards this bottom of this surface, which will, at this point, the values of these model parameters theta 0 or theta 1 will give you the best fit, because as we had already seen, a best fit for a particular data set is when the mean squared error is the lowest. And the mean squared error, as we mentioned before, is the sum of the square of the distances between the actual data point and the estimated curve or surface. So if you keep that distance as the lowest, then it is going very close to your actual data point. That's what it means. So but one thing that we have to be careful about is that since we are taking any arbitrary point, it is likely that we could take a path like this in one iteration, or sometimes we could take a path in this direction, and sometimes this particular point may not be the global minimum but may actually be a local minimum. But it is so we may have to do a couple of repeated iterations to find the best possible fit for our model. A way to measure how well our model fits, one is, as I said, we have to find the lowest cost. But after having found the lowest cost, we also need to make sure that our model is a good fit. And the way we do that is there's a measure called the R squared, and the R squared is measured as is given by this equation 1 minus residual sum of squares divided by total sum of squares. Even though we have this somewhat this equation, there's nothing much here. The total sum of squares is how much the data point varies around its average, which is given by y bar hyphen I, which is the mean of y, and the residual sum of squares is the sum of squares between the actual data point and the estimated data point. Estimated data point is given by this y hat we have here. So when R squared is close to 1, then typically our model is a good fit. That is how we ensure that our model is a good fit. And for lower values of R squared, maybe less than 0.3 or 0.5, we say that it does not have a good fit. Now, so far you have seen uh, regression where we just had a single variable with respect to a single output variable. But typically in real world, we will tend to have, in the real world, we'll tend to have multiple features. So for example, if you're trying to find the cost of a house, it'll probably depend upon multiple factors and features. So you need to look at the location of the property, how many square foot is the house, whether it's close to schools, hospitals, airports, how many total number of rooms the house has, the number of bedrooms, etc. And all of this will somehow be related to the cost of the house. So the same technique of gradient descent is used when we try to estimate a response variable with respect to several input or feature variables. Then this is known as multivariate regression. Here's an example which is taken from this book, Introduction to Statistical Learning by Trevor Hasty and Robert Tibishirani and others, where they have an example where the sales of a product in 200 different markets is measured in relation to the advertising budgets each of those markets in 3 different media, that is TV, radio and newspaper, and the results are shown, how the sales varies with respect to the TV advertisement, how sales vary with respect to radio, and how it varies with respect to the newspaper advertisement. And if we use the machine learning algorithms of R or Python or any of Octave or MATLAB, typically what you will get is you will get a complete description of, you will get a table which will give you the different values for the parameters, how much you should weight each of these different parameters in your model. In our model, current model, we have the TV, radio and newspaper as the 3 input variables, and each of these have to be, you can assume that they have weighted slightly differently to give us the corresponding response or target variable. And these weightings are given by these coefficients here in this first column. And then we have a couple of other columns, standard error and t-statistics, and the 4th column, p-value, is an extremely important column which is provided in any of our Python or Octave's machine learning libraries. And this p-value tells you how whether a particular input feature or variable influences the target variable, whether this input variable is statistically significant. So the way we read this is, whenever this p-value is less than 0.05, then it means that that particular input variable is very significant and it actually impacts the output variable. In this case, the output is the sales. So since TV and radio have a very small p-value, we can say that TV and radio actually influence the sales of the product, whereas newspaper has a p-value which is greater than 0.05, and hence we can conclude that the newspaper does not influence the sales of the target variable, and we can actually drop newspaper in our from our machine learning model and try it out again. One particular important approach that is done in machine learning is, when we have given a data set, the way we we build a model is, we divide the data set into two parts, maybe the training set, which is about 70%, and a test set, which is 30%. We build our model on this training set. We keep fine-tuning the model so that we get the best fit, that is the lowest mean squared error and a very good R-squared value. And then once we think we are sufficiently confident that we have a good model, we then test out this model on this test set, which is about 30% of the data, and ensure that this model actually does fit on unseen data, because it is, if we are just trying to create a model on all the data, it's just going to try and do some kind of a curve or surface fitting, and that is not what we want. What we want our model to do is not just to give us a good fit on seen data, but also be able to give us a good fit on unseen data, or in other words, it should be able to generalize well. There is a third approach which is used, where we divide the data set into 60% training set, 20% validation set, and another 20% a test set. So what happens is, we train a model on the 60% of the data, keep fine tuning it, and test it out on the validation set. So we try out different options. That is, we may try first order, we may try a multivariate regression, we may try second order for the model, or we may try a polynomial, etc. And we try to find the best R squared value for our model. And once we have that, we then take that best model that we have so far computed and try it out on the test set, and ensure that this model also performs very well on the test set. Because typically, when what happens, the issue that happens in this second approach is that we can, by fine tuning our model, we may actually try and give a best fit of the test set, but we have a basic need to ensure that we perform well on unseen data. Okay, so we cannot keep on tuning on and trying to fit on even unseen data. So we try out on the validation set, and then finally make sure that that it also performs well on the test set. And once we have that, we can say that we have our model does well. Okay, so far we have seen what is known as regression of a continuous variable, because the age and salary was continuous. Similarly, the sales with respect to the advertising budget in TV, radio, and newspaper were all continuous. Another set of regression problems is called classification, where the algorithm will have to determine one of two classes or one of many classes for the target variable. When we have just two classes, it's known as binary classification. When we have many classes, it's called multi-class classification. One important class of regression algorithm is known as logistic regression, which is essentially used for binary classification. So, for example, when you want to, you have data on a tumor, the size and shape and other aspects of the tumor, and you want to determine whether the tumor is cancerous or non-cancerous, that is benign, or you have got several males, and you have the subject and the content, and you want to look at that and determine whether the male is spam or not spam, and so on. This kind of problem, where you have several input variables or features or predictors against a target variable which takes one of two classes, is known as classification. We tend to use logistic regression for this. And how do we do this? Fortunately, there is a very useful function, mathematical function, in which does exactly this. That is, it is a continuous function, but it takes, you can say it takes one of two values. As you vary this x-axis, you will find that it goes between 0 and 1, and it is continuous. It's not a step function. So typically continuous functions are pretty useful in machine learning, because you can take the derivative of it at all points. So this is represented by this equation, but we can ignore the equation, but just need to understand that you provide some parameter for some parameter z. If you use this function, it will take one of two values. And even though it seems that this value is not exactly 1 here, what is assumed, that is, when this function takes a value greater than 0.5, then it is considered as 1, and anything less than 0.5, it is considered as 0. Okay, and so we can use the sigmoid function to model any problem where we have one of two classes. And such classification problems, we need to be able to identify how well we are able to classify. And there are several important metrics that help us to do this. One is known as accuracy. So when we are trying to classify, you will find that you will be able to correctly classify positives as positives and negatives as negatives, but you will also falsely classify positives as negatives and negatives as positive. So if you take the total number of positives plus total number of negatives, that is what you correctly classified, it was a positive and you classified as positive, it was a negative and you correctly classified as negative, correct classification, versus all the other positive, correctly classified as positive, incorrectly classified as positive, correctly classified as negative, true negative, and incorrectly classified as negative. So if you take the correct classification against all the total number of measurements, that is called accuracy, the fraction of all classes correctly classified. Then we have something called precision. Precision is among those you have identified for the cancer as positive. You will find that some of your algorithm classified tumor tissues which are actually cancerous, but also incorrectly classified tissues which are not cancerous as cancerous. So that is called false positive. So this fraction of true positive over all the positive, that is the true positive and false positive, is known as precision. And finally we have recall, which is also known as sensitivity or true positive rate. Here what happens is you have the true positive and you also have the false negative. So what false negative is, it is not cancerous, but you have incorrectly classified the negative as a positive. So it is known as sensitivity. So recall is true positive divided by true positive plus false negative. So far we have seen some basic machine learning algorithms. Basically we have seen regression of a continuous variable, where we saw a toy example of age versus salary. Then we looked at what is bias and variance, and what is a good fit, what is an underfit, what is an overfit. We also saw multivariate regression, where we had several features against one target or response variable. And finally we saw classification problems, where we use logistic regression for binary classification and some of the measures for this classification. So you may start to wonder what exactly, machine learning, it looks like we're trying to minimize, trying to fit the data as close as possible. But machine learning is not simply curve fitting. We're not trying to fit a model which mimics the data as close as possible. What we're trying to do is we need to be able to generalize our model such that it performs well on seen data and also unseen data. As long as the data is coming from the same population, we would like our model to be able to make the exact prediction and inferences on even unseen data. So it is not curve fitting. It is also not optimization. It is not just that you're trying to find the lowest mean squared error. So you could see that in the when we had this higher degree polynomial, the mean square error is lowest, okay, but that is not a good fit. Clearly a good fit is only when it is able to generalize well on this data. So it is not optimization, it is not curve fitting. Machine learning tries to find the most general solution, so it should be able to generalize on even unseen data as long as the data comes from the same population. So this concludes this first part of this machine learning in plain English series. Thank you for listening.